So let us understand this problem, knapsack 2, and why is it different from the previous versions of knapsack which we have done. So the question says there are n items numbered from 1 to n. Item I has a weight of wi and a value of vi. And there's a person named Taro has decided to choose some of the n items and carry them home in a knapsack. The capacity of the knapsack is w, which means that the sum of the weights of items taken must be at most w. Find the maximum possible sum of the values of items that Taro takes home. And when you read the question, it's clear that it's same as the previous versions of knapsack. Okay, so it's same as the previous versions of knapsack. You will be given some n items, and you need to pick a subset among these. And we also know how to handle subsets in DP by taking position in the state. Okay, so we'll be soon learning about how to handle subarrays, subsets, and matching two sequences, etc. in the DP. I guess matching two sequences is already there in one of the videos. The video name is probably 2-pointer DP. You can search it like how do I do it, etc. And coming to the subset thing, in subset the idea is, the state idea for maintaining a subset is maintain the positions. So inside the recursion you would maintain positions and whatever the extra restrictions are there, and don't try to call it any kind of 1D, 2D, 3D stuff. How many restrictions, that many D's would be taking. By default it would be, there would be a single dimension. If we require more stuff we would keep it in the recursion, otherwise no. Okay, so that's how picking subsets work, and while writing the code I would elaborate on this. But for now, how is this problem different from the previous version of knapsack? So as you can see, inside the recursion, what would be the states? What would be the, like, what would you be putting in the state? First thing, you would put the position. You would put the position I. Like on this I you would decide whether you are picking I or not picking I. Based on that, it would move to the next transition. But also you are putting the weight, and we have this problem of weight here. Weight tends to 10 power 9. Weight here tends to 10 power 9. Can you put 10 power 9 in recursion? It's not very feasible, and to get a clear idea of it, forget about recursion. Can you make a DP array of 10 power 9? Can you make a DP array of size 10 power 9? No, right? And positions are also 100, so it would be 10 power 11. As we know, hardly we can make arrays of 10 power 8, which is also not that great, I would say. In most cases it would be better if you solve these kind of problems using greedy, but for this particular problem greedy doesn't exist. So how would you do this? How would you deal with this? Like 10 power 9 cannot be kept in state. The only way you can do knapsack is this thing. Like the only way which you know probably is only this one, right? Now the idea behind a DP optimization technique, whose name is state rotation. The idea name is state rotation. This can be used. This is also known as inverse DP, because I'll be telling you like why is it called inverse DP and all. So here the thing is, we deal with inverse functions. So let's say f of x gives you y. F of x gives you y, but due to some reason you want to find y. Y is forever the answer. You want to find y only. But if let's say calculating y is hard due to some reason, due to this formation, calculating y is hard. What if I know f inverse, which is a much simpler function, and I know f inverse of y is equal to x. If f of x equal to y, f inverse of y would be equal to x. So I know this, and compared to this one, this is a much simpler function. So what I can do is for different values of y, I would be checking which particular value gives me x. I would substitute different values of y for some possible values in some possible values of y, some possible value p. Let me write it differently. For some possible value p, not positive value, possible value p among all the possible values, I would substitute every p in the f inverse, and whichever p gives me the optimal answer, which is x, it would be the right answer. So here you are doing the same thing with inverse, right? Here also recursion of I and weight gives you value. Now if you rotate this state, which is the problematic state variable here? W is the problematic state variable. W is tending to 10 power 9, which is giving you a problem. What if you invert this recursion, some recursion inverse of I comma w, this would come here and this would go here. If you rotate it this way, recursion of I comma v gives you some w, for every value it's giving you some w. And can I say that in this case, if I'm trying to find the maximum value, this particular w should be the one, which exactly fits in my knapsack capacity, which is capital W. Okay, this particular w, this is the lowercase alphabet w. If this fits in the knapsack capacity, this w is optimal. I need to find the maximum v for which the w fits in knapsack. And also can I say that if there would be multiple w's, let's say to get a value v, there's w1, w2, w3. Which one should I consider? I should always consider the most minimum w. Like, what is, let's say value is 50. Let's say 50 is attainable using weight 6, 5 and 2. Which would be better? 2 would be better to take. With this I can always ensure that since I'm picking the minimum weight, the minimum weight should basically fit in the knapsack. I need not maintain a constraint for maximum weight. Let's say knapsack capacity is only, let's say 4. In that case these two would be anyways pruned. Does that mean I cannot make 50 anytime? No, right? If the minimum I am getting via 50, like to make 50 the weight 2 is enough and 2 fits in the knapsack, it's over. I can always make 50. So I need not check any other weights, I just need to put the minimum weight. Okay, so that's the idea of inverse dp or state rotation. Whenever a state gives you a trouble, just rotate it, or like this is also not always possible, you need to observe properly. First thing is greedy is not possible. That's the biggest hint. Greedy is not possible. And one constraint which is part of this recurrence relation, which is outside this recurrence relation, has smaller constraints, right? Okay, one of them has smaller constraints. It has just 1000. So probably you can rotate it. It's just an idea. If you are how to get this intuition at the first point. After writing the original recurrence relation, which is the simplest form, like the original function without inverting it, you need to make few observations. First thing, with the outer value which is there, is there any way to engineer the state in such a way that these inner values which is giving you trouble is getting eliminated? Is this inner value getting eliminated? That's the first thought process. And the second thought process is the constraint small enough? Like, can you put this outer value here? And the third most important thing is, after putting all this, can you write the actual transition for this? Like in this case it's the minimum, right? In this case it's the minimum, right? So can you write one such transition like this, like you have to pick the minimum, etc.? So if you can do all this, probably you can rotate the state by finding the inverse function. That's the core idea. So if you had to code this up, first let us write the normal knapsack just for fun, just to show you the recursion of the knapsack, how it works. Or else let's skip it. Okay, let's skip it. Just some basic template setup, and I hate writing long every time, so, and I hate writing LL also, so I usually replace this with long, and I have a habit of writing NL always, so just basic stuff. Okay, so coming to the recursion, you know the basic knapsack recursion, which takes the position and which takes the weight, but we cannot take the weight. Okay, so I need to pick the minimum weight always. This recursion would pick the minimum weight always to make the value v. So if you want to write it in the forward manner, which is, I don't know, push dp or pull dp, whatever you call it, you would need an extra parameter v every time. Like you would need an extra parameter capital V, let's say, every time. And then you can write things like this: v is equal to capital V, then return 0, etc. But there are too many parameters, and why to involve an unnecessary parameter? So I am doing subtraction. So if v is less than 0, that means you have already made some value which is less than v, so you cannot reduce the value more. So in that case, return minus infinity. And let me define minus infinity. Constant infinity would be equal to 1e9. Okay, we are not maximizing, so it should be plus infinity. Sorry, my bad. So if v becomes less than 0, it is impossible to make the value. It is impossible to make v again. And if I is equal to n, if I is equal to n, and that means you have reached all the subsets. And if by this time v becomes equal to 0, that means you have found a valid subset. You have found a subset that makes the value v. So this is a success case, return 0, and else once again it's a failure case. Okay, and we haven't defined n yet, so let's define n also. Next, this was about the base cases. So usually in maximization or minimization problem, the success cases return 0 and the failure cases return infinity in case of minimization and return minus infinity in case of maximization. Okay, how does it help is, automatically when you return positive infinity, when you are like minimizing, it won't be getting picked. Okay, positive infinity, recursion would never pick the positive infinity because it would obviously pick the optimal choice. Positive infinity cannot be ever an optimal choice, so we return this positive infinity. Otherwise we would return 0, okay, for the success case, and we need to minimize weights, so return minimum of some w of I. We haven't made this array w, so let's make one. What was the number of stuff in the w? Capacity is 10 power 9 and n is 100. N is 100, so w also would be 100. Let's take it 101, and int value would also be 101. Now we need to pick a minimum of, either if you pick something, its weight would get added, and you would move to recursion of next item. You can either decide, you can make the same decisions again, you can choose to pick or not pick the next item, and value that you are accumulating would be the value of the current item, so v of I. Okay, and this v is already something, so let's take it this way. Weight of I, v minus, this is the problem. See, I am habituated to writing it in the forward direction by adding stuff. Okay, so this would be the next recursion which would be getting called. So this is the transition, and if I don't pick something, nothing would be added. I would move to the next recursion, I would move to the same choice for the next item, I would move to next item, and value also won't change. I'm not picking anything, so the value also won't change. Now this recursion, what does it do? It returns what is the minimum weight that must be picked in order to make the value v. So this is what this recursion does. Now coming to the next thing, this is basically the f inverse. This is basically the inverse function, isn't it? Now inverse function acts differently than the main function, like not the main function, the other function, the normal function. What is it? In inverse function, to get the right answer, you need to substitute values. Okay, so what is your, I've already told you possible values. What are all your possible values? So can I get a value 0? Yes. If I don't pick any item, I can get a value 0. Yes. Next, can value be negative? No. And can I get a value 1, maybe 2, 3, 4? I can get all of them, so on till what's the maximum value which I can get? I can get sigma val I, where I is equal to 0 to n. This is the maximum value which I can get if I pick all items. If I pick no items, it's 0. If I pick all items, it's the sum of all these. So this is my search space for the inverse function. So I would take all the possible values, which are value is equal to 0, value less than or equal to some max value, and value plus plus. These are all the possible values. And coming to the computing of max, first thing, let me take n, let me take capital W. Okay, these should be global because the recursion is also using the same things. Int W, so n is already there, c in n, c in w. Next, I would be given, what would I be given? I would be given weight of I and value of I. So for int I equal to 0, I less than n, I plus plus, I need to w1 and v1. So weight is given before, weight of I and value of I. Okay, value of I. And max hasn't been computed yet, so here itself let's compute max. Max is equal to 0, and whenever you take a value of I, just add it to the max. Max plus equal to value of I, max plus equal to value of I. So this is the value of max. Now we have max also, so you can substitute this. So if recursion of, you'll always be starting from 0 only, right? You'll always be starting from 0 only, right? And this is a, now we are calling the recurrence function directly. We won't be doing that, we'll be DPing it. So it would be cached recursion. So to cache it first, you need to call the recursion for I comma max value first, so that everything is cached once, not I, 0 comma max value, always starting from 0, and max value. This is what you should cache first. What do I mean by the word caching is, the first time when you call the recursion, nothing is computed. So according to the DP it would compute. According to the DP it would compute all the stuff. Okay, using DP. Like this is also the first time when it's called with DP only. If there are overlapping subproblems, it won't be recomputed. But when you're running the same recursion in this for loop, this recursion should not take any time, extra time, apart from this DP thing. This would take some O of n square, right? Some quadratic time. So here it should happen in O of 1. And why would it happen in O of 1 is, the first time when you call this recursion with the max value, every state is already computed. Every state is already computed. The second time when you call it for all the different values, whenever you call it for all the different values like this would give the answer in O of 1. This would give the answer in O of 1 because it's already computed. It's already computed. Every DP state is computed. So it would just go through that if statement where you're checking is this DP state is already computed or not. If it's already computed, do not recompute it, directly return it in O of 1. So that's what happens in all the cases inside this for loop. So this check, you can say it's not taking any time. Okay, so this would be the check. And if the minimum weight is less than the capacity, less than or equal to the capacity, then the answer is value. Okay, answer is value. And if it's not possible for any value, its answer is 0. Answer is equal to value. So, and we need to see out this answer and indel return 0. This is what we'll be doing. But since you can notice that we haven't DP'd this, let's run the test cases once just to check if everything is passing. Yeah, everything is passing. Okay, now we need to DP this looking at the constraints. What's the total size of n? What's the total size of positions? Positions can go up to 101. This can go up to 1001. And if you DP this, it would be just doing a memset first. DP -1 size of DP, and here you would write if DP of IV is not equal to -1, in that case it's already computed, so return DP of IV, and otherwise compute it, and before returning it just store it in this. Okay, everything seems fine. Let's run it once again. Okay, yeah, so this is a less common optimization, the inverse function thing. And if you want to optimize this further, there are ways, and let me tell you one such way, which is called something called rolling DP. Rolling DP, in the sense, I guess most people already know this. I'm sure most people don't know this one, and I'm sure most people know the rolling DP version. Okay, it's not a version, it's just the iterative code. So the rolling DP is nothing but if every time you are requiring only up till I+1, that means at every particular step, at every particular level I, you are requiring only level +1, which is the next level, I+1. So Do you need to maintain a grid or an array with 2 rows? Obviously an array with 2 rows, right? You only need to maintain an array with 2 rows. This is where this idea of second optimization comes. If you already know this, you can quit the video here itself. So here, instead of storing it this way, okay, let me tell you the idea of rolling DP. Whenever, let's say, state depends on very few next states, like in this case, this thing only depends on I plus 1, or let's say something depends on I plus 2. Okay, in that case, you don't need to store the whole grid, right? You don't need to store the whole grid. 2 rows are enough. So when I requires I plus 1 and I plus 1 is already computed, I would directly access I plus 1 from here. I would directly access I plus 1 from here, from the ith row. Now the question comes that if this is the case and I'm accessing I plus 1 from I, what if I have to move to the next I? Let's say this is I plus 1. This is the, let's say, nth row, and n minus 1th row. Here this is I plus 1. This access is happening, but I need to compute the n minus 2th row also, which is, let's say, I is here, I plus 1 is here. So let's say I want to compute n minus 2th row also. What would I do? So the idea for this is, see, I have I already computed, right? I have I already computed. So I would swap I to here, like not swapping. I would just copy this nth row to n minus 1th row and empty the, like, I would copy this n minus 1th row to nth row, sorry, my bad. I would copy this n minus 1th row to nth row, and n minus 2th row would be needing this nth row. So I always need 2 rows only. If the last row is computed, I can compute its previous row, then I can copy this last row here and compute this previous row. Okay, so that's the idea. You would move in this direction. So if I want to do that, I should be converting this to iterative code. Okay, I should be converting this to iterative code. Let's see how to do that. All this is not needed. We'll rewrite all this stuff again. For now, let's comment it so that it stays for the reference. So in this case, you would require the next DP row. And which state are you eliminating? You are eliminating this I plus 1. So you don't need this 101 size state anymore. Okay, this is next DP and this is DP. This is also taking the size. And yeah, we don't need recursion, so let's take it in solve. And this time I would try to write a forward code. Forward code in the sense we take the initial value as 0. So forward and backward, what I mean is, some people call it push DP and pull DP. Okay, some people call it push DP and pull DP. What it basically means is, if you are going 0 to V, 0 to a particular value V, by adding something Vi to 0 plus Vi plus Vi, if you are doing this is according to me the forward. I don't know this terminology properly, but I've heard people using this. Okay, I call it forward DP. So from 0 to V you are going this way. So this is one way. Other way is which we wrote here. You already take the V and do minus. So some people take here also n. Some people take n here, recursion of n. This is also valid. You can solve it via this particular recursion also. But that's reverse. That idea I generally don't like, because it's not very intuitive for me. I don't take n here. I always start from 0 here. It's not intuitive for me. If it's intuitive for you, I would suggest to go with this only. And yeah, second thing is that sometimes you need to add extra parameters, which is annoying. That's why I prefer sometimes writing these kind of things in reverse. Like here, if I had to write a forward DP for V, if I had to write a forward recursion, I would have to take an extra parameter int capital V. And here also, if this V would have matched with capital V, I used to return 0, etc. It's easy to figure out these kind of things, but yeah, why to add extra parameters? Now coming to this thing, I would like to use forward DP only. That means I will be going from 0 to V, which is comfortable for me now. So I have taken this int V. Now the thing is, if for int value is equal to 0, value less than or equal to V, value plus plus. So here what we had done was, if something is impossible value, we would put it as -1. So next DP, first we need to compute the last row, and using the last row we would be computing the last previous row. So next DP of value would be equal to infinity. Okay, it would be equal to infinity. But if next DP becomes equal to this value, or else why to put it this way? Okay, if it becomes 0 only, let's say I'm writing backward DP only, I'm doing subtraction once again, so that this remains intact with this. If next DP becomes 0, that means this base case hits, then in that case it would be 0. I would be returning 0, which is the success case in case of maximization and minimization problems. Now here in this case, the first computed state is, you're calling this recursion for 0, right? So 0 is the last computed state, 0 would be the last computed state, and n-1 would be the first computed state. So int I equal to n-1, I greater than or equal to 0, I minus minus, and this would be in the forward direction for int value is equal to 0, value less than or equal to V, and value plus plus. And here this time we cannot prune the nodes like this outer thing we cannot do, so you need to check it here itself. If value minus value at this particular index is greater than or equal to 0, then only take it, prune it inside this for loops. So DP of, this time we are computing the current one, DP of value would be equal to, what would it be equal to? It would be equal to minimum of weight of I if you pick it plus next DP of value minus V of I or value of I. Okay, and otherwise if you don't pick it, nothing would be added, and this would directly be equal to next DP of value, nothing is changing. And if this is not true, value minus value of I, that means this particular value is not takeable. In that case the previous state would be retained. DP of value would be equal to next DP of value. Okay, implementation wise you can separate this else statement and put the next DP as a default value, so these kind of things can be done. And to copy, we have a function. After you compute this particular row, you can just do mem cpy, and it will take from next DP to next DP. You need to copy the previous DP, so this would be the destination. dp would be the source, and how much should I copy? Size of dp. This is what you'll be copying. If you are using vectors, you can directly assign them to each other, or you can use move function. Both are fine. And next dp of this particular value would be the answer, because here also recursion of value is the answer. Okay, so if you are not understanding this, it would be better to practice the same thing on some simpler problems, but the core idea of this problem is this. Even if you have even if you submit this would work. Okay, so now just rewrite the if statement. What we need to rewrite is, if solve of value is less than or equal to the capacity, then value is a valid answer and cout answer. Let's see if this works or not. And once again it passes. Both of the solutions would pass, even the recursion one would pass. And I would prefer to write the recursive solution in a contest, because it's easier, faster and clearer to write rather than converting to this approach. This approach can be used when you seriously want to space optimize, like the constraints are in such a way that you have to space optimize. Okay, let's say some dimension is making it 10 power 6, but the time is fine, right? 10 power 6 operations, time complexity wise is fine, but dp wise it might not be that suitable. Maybe you want to optimize some cases, then you can always prefer this, but yeah, the recursion one would also pass. So let's try to submit this and see what happens. So if I submit this, I've already submitted fair amount of questions. Actually this is not a main account, it's a bot account, and we have a runtime error. What could potentially cause this runtime error? We have almost everything right. Define int long, define indel n and w are there. Weight and value is also there, and the dimensions are right. 101, and we have written solve function. Did we mess up something? Did we mess up solve function somewhere? Okay, wait a minute. We were doing a very silly mistake, which is each value is 10 power 3. So 100 into each value. What would be the maximum sum? This is at max the sum, right? The at max what you are accessing is the sum. So the sum would be, first thing it's 10 power 3 and one more 0. Is it 5 zeros? 1 2 3 4 5 zeros. Yes, done. That was a small mistake which we were doing. Now it's fine. So let's submit this. If you had taken a vector or something, it wouldn't have been like a big deal, but I prefer taking global arrays because they are comfortable for me. Once again TLE, this time it's a TLE. Next TP assigning infinity, next TP of 0 equal to 0. could be causing this really now? Dimensions are proper, 100 into 1000, fine. Then we have this part is main function, alright. So taking the input of this weight and value, and also okay, done. So this is the problem, this is the O of n thing. We shouldn't call it this way, remember, we first need to cache everything. So we need to call solve of mx first, and once solve of mx is computed, next dp of mx would be the answer, right? So next dp of value should be less than or equal to w. So these are the silly mistakes, and you can really avoid them. So most of us make these kind of mistakes, and if you verify your code once again, it should be fine. Once again, let's submit. This time it should be proper. Let me check once again. Next dp of value, fine, done. So this is accepted. Okay, so the core idea which we have discussed was inverting the function. Okay, that was the first thing. And I'll let you know that it's always better to write the recursive code. Move to a iterative version only when you want to write rolling dp. Okay, only when you want to write rolling dp, move to a iterative version of the code. In most cases, the recursive version would work. It, as some people say, it won't give any stack overflow or something. If you are in CPP, because CPP stack is like fairly huge compared to the one in Java, so in most cases you won't require the iterative solution. Okay, so only when you want to optimize on space you can write an iterative solution, but there are many more optimizations like this one. Okay, there will be more optimizations on the recursive code itself, which would make the recursive code work. If we had not done this optimization, even the iterative code would have failed. So that was the complete idea of inverting the functions, inverting the recursion functions to fit in the constraints. Okay, so that's it for now.